Hello, hello, hello. So, the time has come for another project's Euler problem. I guess we're a quarter of the way through the first 100 now, that we're on number 25. So, this one's just called 1000 digit Fibonacci number, and it gives us the definition of the Fibonacci sequence, which I think is, well, it has come up before in problem 2 of Project Euler, so we should be familiar with it. And if you're watching these videos, you've probably seen it before, but here it is. And then the question quite simply is, well, the 12th term is the first one to contain 3 digits. There it is at 144. And then what is the index of the first term to contain 1000 digits? And with this problem, there are lots of ways to do it, and I'm going to show you 2 ways that I've managed to do it. So the first one is just going to be a brute force way, which is still pretty quick at sort of 100 milliseconds, and there's a slightly cleverer way using maths that lets us do it in less than a millisecond, which I think is pretty cool. So let's go through the brute force way first. And I guess I'm doing this a bit differently to usual in that I've kind of written the solution and I'm going to talk through it rather than writing the code, just because I feel like that might be a bit quicker. Might make the video a bit better. I don't know. Anyway, so the way I did this is I just looked at how did I generate Fibonacci numbers in problem 2. So problem 2 was basically just add up all of the even Fibonacci numbers less than 4 million. I assume that's what it was anyway, based on the code I've written. And I guess go and watch that video to understand why this works to generate Fibonacci numbers. So the point is I can sort of, and yeah, I've re-indexed a little, and importantly I've used big ints rather than ints, because we're getting to some, because it's 1000 digits, that's actually the number there, the first number that's over 1000 digits long. So that's why I've had to use big ints, and I've re-indexed as well. And then literally all we do is we take our iterator of indexes, which I guess are just 1, 2, 3, blah, 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 zip it with our iterator of Fibonacci numbers, and just finds the one number such that the length is equal to 1000. It's not that exciting, and it just kind of works. Great. Now, the clever way is much more interesting, and it relies on something called Binet's formula. So this is something that's been known about for, I guess, hundreds of years, and some people came up with this formula for the nth Fibonacci number, which is in terms of the golden ratio. And I first saw this when I was doing A-level maths at school, and you basically just pretend like, oh, let's pretend it's a geometric series and pretend that we're sort of adding up two geometric series to get the result. Anyway, we end up with the golden ratio to the power of n, and then I guess it is because it says conjugate. To me, conjugate kind of makes me think of a complex conjugate, so I'm going to call this a radical conjugate, just to be on the safe side. And this is the sort of a way of working out the Fibonacci number. I once used this in an interview, actually. When I was getting, I think, my first job. I didn't get the job in the end. I got a different job. But yeah, I think they wanted me to do like tail recursion or iteration or something rather than whip this thing out. Anyway, so the point is we have like quite an efficient way of computing one Fibonacci number, and then so I've just written out what's in Wikipedia here in terms of phi and psi, and I've just got back from a holiday in Greece, so I know all about Greek letters now. So this is the nth Fibonacci number in, I guess, a scala draw, and because we're dealing with large Fibonacci numbers, we can essentially ignore. Can I do a different colour? Yeah. So we can essentially ignore the contribution from psi, because when n is large, psi to the n is going to be really small, because the absolute value of psi is less than 1, and n is an integer in this world. And like, I guess for some intuition, what I quite often like to do is maybe go to Desmos and just have a look at why this is the case. So we can see that if we've got a number that's got an absolute value that's sort of less than 1, we can see that as it gets bigger and bigger and bigger, as n, which in this case is x, gets bigger and bigger and bigger, the value gets smaller and smaller and smaller. And then if we go to the other side, so if we go past -1 here, then the opposite happens, and there's this sort of equilibrium point around 1. And like Desmos, the reason Desmos is doing this little like dotty, I think, is that for sort of fractional values of x, this kind of isn't really defined. You kind of have to go into complex numbers and things to make this work. But anyway, I thought this might just give some intuition. And before Desmos, I used to use, just because I mentioned A-level stuff before, I used to use this calculator to do this sort of thing. It's a great little graphing calculator. I've still got it actually somewhere. Anyway, point is, we can basically get rid of this bit. So we can say that f of n is approximately 1 over root 5 phi, where phi is the golden ratio, to the n. So we'll say those are approximately equal. And it's, in fact, I think it's asymptotic. Okay, and then, well, how the heck does this help us in any way? So the answer is that there's a little fact from maths, which is if I take the log of base 10 of some number, let's call it a, and a has d digits, that is horrible handwriting, isn't it? Wow. Then I know that this is going to be in between d and d minus 1. And like, I guess we would do, I guess what we would do here is to sense check it. We could go into Scala and just check it for some values, but hopefully it's kind of obvious, because if you think about something like, I don't know, if we have like 999, that's got 3 digits. If I take the log base 10 of that, it's just going to be kind of a little bit less than 4. No, sorry, it's going to be a little bit less than 3, because if we got all the way to thousands, then it would be exactly 3. I think one of these should be, if it's got d digits, I think one of these should be have an equality on it. I think it's this one. Anyway, the point is we can start using this formula a bit later. So what we're going to do is we're going to take, because we care about the number of digits, we're going to take log base 10 of both sides of this expression here. So f of n is on this side, and then we can say that that's approximately equal to, well, I guess n log base 10 of, and I'm just going to do this all in one step, I guess, using basic logarithm rules, and then we're going to obviously subtract off 1/2 of, I guess I didn't need to take the 1/2 down, but I have now. So here we are, log base 10 of 5, like that. And then, since what we care about is the number of digits being equal to 1,000, what we can do is use half of this inequality. I don't think it really matters which half, but let's use the right hand half of it, like this, and we can replace, so for us a is going to be equal to f of n, and I think this approximation, I should really use inequalities again here rather than approximately equal, but I can't be bothered. um, so we're just going to say now that n log base 10 of phi minus, I have to write all this out again, don't I? I should have kept the square root, I guess. Log base 10 of 5 has to be greater than or equal to, for us d is 1000, so I guess this would be 999. Although, no, actually, let's just keep it generic as d, and then we'll substitute in 1000 at the end, actually. So d minus 1. Cool. Then, since what we want to find is n, let's just get n on its own in this inequality. So n is going to be greater than or equal to, let's see, so d minus 1 plus, excuse me, 1/2 log base 10 of 5, and we're going to divide all of this by log base 10 of phi, like this. And then what we're going to do is we can now say that we want the version of this such that what do we want? We want to find n. Basically, I'm trying to figure out if we need to take the floor or the ceiling of this to get the answer. And let's have a think. So it's going to be this is the sort of lower bound for it. So we want to take the ceiling, because if we took the floor, then that would be the value of n before we get to 1000. So we want to take the ceiling of this. Let me just get my eraser out, and that's what our n is going to be equal to. I might be wrong about that, to be honest, but let's see. So let's go to the answer that I've written, and yeah, it was the ceiling. So let's see. So d minus 1 plus math log 10 of 5 over 2, d minus 1 plus, yeah, and all over, yeah. So that's the same, and yeah, the reason this works is I first made an approximation. I first used this full-on Binet's formula. I then used an approximation because we're dealing with large numbers, and then I used the fact that if you take the log base 10 of a number, that basically tells you how many digits it's got, and then I just did some algebra to rearrange it so that we can find our value of n. And yeah, I mean, I think personally that this one is way easier to understand, and this one was harder to come up with, but it's, you know, way faster. So there's advantages and disadvantages, and like I know this is the correct answer. I've already sort of checked it, but I guess it's somewhat become a tradition for me to just double check the answer in the video, like this. So let's see, and that works. I mean, I'm not sure I explained that. I'm not sure I explained this math stuff that well, but hopefully it makes some sense, and hopefully it shows that some of these problems you really can do with a calculator. Like, there's no reason I couldn't have just used my version of this calculator to work this out, other than the fact that I don't have the 4 AAA batteries that it requires anymore. But I think I use them for a TV remote or something. But I do still have the calculator. Anyway, I think that's probably a good place to stop, so I'm going to stop. Thank you for watching, and yeah, hopefully this made some sense.